Okay, here you go. Those are the sections. Some material, for example, here you go. Remaining of chapter 17, right? 17.-7 to 17-8 and 9. Chapter 33, 1, 2, 3, we skip 4, 6. Oh, no, we didn't skip 4, we just put it in a different order. Here you go. 1, 2, 3, 4, 5, 6, 7. Let's take a look here at the waves 2. So let's take a look there. 7, 8, 9, and 10. We didn't have 6, right? Yeah. Did I skip 6? Hey, wait a minute. The order here, okay, this number here refers to the old edition of the book. Let me fix that. Intensity of sound. Okay, we skipped this one. Let me see if I have the right. Okay, this number seems to be of my old edition. Let me make sure here. That should be the right numbers. Let's see here. Start at 7. No, we are not skipping 6. 6 is bits. We did bits. Okay, so there's a mistake here. Okay, most likely those numbers here are the numbers of my older edition. Let's see here. 6. Yeah, those numbers are for my older edition. So let's go back there. We will include remaining of chapter 17 that does not show up. That did not show up in exam 1. Okay, so what was that? Intensity of sound. Okay, that was the one that we skipped, 17.4. Okay, and okay, yeah, 5, 6, 7, and 8. Okay, 5, 6, 7, and 8. 5. Yeah, that's according to my older version, the 7th edition of my holiday resnick. Then later edition they changed the order of the sections. So here goes. So sources of musical sound. Okay, sources of musical sound 17.5 in the new edition. 17.5 sources of musical sound. 17.6 was bits. Then we did the Doppler effect. -17 Doppler effect. Okay, that was in the older edition, 17-7, 17-7 in the older edition. That's 17-8 in the older edition, and so on. -9 in the older edition. 17-7, and what else? And 17-8. -8. Supersonic speed shock waves. Supersonic speed and shock waves. 17-10 in the older edition. Okay, that's oh, it's 17. Here you go. Now, those are the sections for 17. Can we include the following sections? Okay, the remaining of chapter 17. Okay, chapter 33. Electromagnetic, here you go. Let's go for electromagnetic. So it's chapter 33 here. You go. Electromagnetic waves, radiation, energy transport and Poynting factor. Okay, radiation pressure, polarization. I did a different order, right? For reflection and refraction. Okay. 5, 6 total internal reflection. We did that. And then reflection by polarization. No, it's not reflection by polarization. It's polarization by reflection. Here you go. There's something wrong here, right? Polarization by reflection. You can get light polarized just by reflecting them at a proper angle. Just by reflecting them at a proper angle. And go, let's see here. That's remaining of chapter 17. And then we're doing chapter 34, true, for the exam. And what's that? Chapter 34, images. Okay, 34-1. Let's go copy and paste everything here, right? 34-1, 34-2, right? 34-1, 34-2. Okay, we're going to skip 34-3. That's a little bit difficult. Okay, so you skip 3. 34-4. Seam lenses, optical instruments. 34-4 and 34-5. If you want, you know, the 34-6 is the proof of the other of the equations that we used previously. Okay, we're not going to cover that because it's very lengthy, but it's not difficult to to understand it because it involves just geometry, geometry basically. That's why it's called geometrical optics. 3 proof 345. Okay, so we can stop here, and now let's put the titles here. Images and plane mirrors. Images, plane mirrors. Spherical mirrors. Thin lenses, that's what you're going to do now. And optical instruments. Those are the sections that you have to worry about tomorrow's exam. And we start doing that. This one here, we're going to do that, and that's when you finish the material for the exam. Let's take a look at the schedule here. Schedule classes, P39. That's the latest schedule. Okay, 34 images. Wait a minute. I already have it here. Nope. Let's see. Make it look nice here. Meeting number. Here you go. Now we have enough space here. Good. Images interference. Today is the 29th. Speed of sound. Let's say, here you go. Speed of sound. And let's not forget to, for the exam, I'm also including the labs. The exam one was this one here. So we should review the material for the notes for standing waves 1 and 2. Labs. For standing waves 1 and 2. On canvas, this on canvas, yeah. Good morning. Okay, can you please? Okay. Okay, I'm posting everything on my Google Drive. Okay, if you have access to it, and I just did that yesterday. And do we have access to the Google Drive, Ismail? Just yesterday, I posted there in the Google Drive, the share folder. You know, and let's include the standing wave 1 and 2 and the speed of sound experiment that you're going to do today. You know what? No, you know what? I'll give you a break here. Let's leave the speed of sound experiment for the next lab, okay? For the next exam. Here you go. Tomorrow is the exam material for the exam 2 labs. So we need to see here. Following topics. Let's put here the following topics, right? Review the material for standing waves 1 and 2. To lab. Many of chapter 17 that didn't show up in exam 1. Chapter 33 and chapter 34. We're here right now. Okay. Any questions? We have 25 students here. Yeah, it's lots of things, right? And let's go for our next topic, which is scene lenses. That equal scene lenses right in here. Okay, so don't forget we are talking about thin lenses. We are not talking about thick lenses, and there are also spherical lens. Image and plane thin lenses. Here you go. They also end up being spherical lenses. So how is a spherical lens formed, right? The same way that a spherical mirror is formed. You go ahead, get a spherical surface, a glass spherical surface, you know, and you get a second glass spherical surface and intersect one with another. What is left here is a convex lens. Okay, here you go. What is left here is a convex lens. This type of lens, depending on the refractive index surrounding it, is going to be a convergent lens. You have, you know, this surface here. Here you go. This, let me put something else here for you. This spherical surface, by the way, has a radius of curvature R1. And the other spherical surface, let's use the notation of the book, that's better. Here you go, lowercase r, not uppercase, lowercase r. Lowercase r1. And then the other spherical surface has a radius R2. See here, that's gonna be somewhere around here. Okay, so even better, I'm going to do like that. Here you go. And the other one is going to be like that. R1 and R2. So that's what's going to be left over, right? Here you go. I'm going to copy this one and paste in another figure. Here you go. Uh-oh, it's not the other one. Let's do this way instead. Here you go. Just move a little bit. Like that. I don't like that. Let's do it in a perfect way, right? Here you go. I'm gonna do that from scratch again. Here you go. R1. And then I'm gonna copy what I have here. I did a little trick here in this drawing. Oh gosh. Good. Ungroup. Ungroup. You go. This one here. I'm gonna paste. Oh, huh. Interesting. That's okay. Here you go. That's what I want. It's not doing what I want. Oh gosh, what a shame. Okay, so let's gosh. Yeah, okay, let's leave this way. That's good enough for me. Here you go. 2 more students coming. Here you go. Well, there is an equation for that relates the focal distance with the refractive index of the surrounding media. The index of refraction, not of the surrounding media, but the index of refraction of the material. Okay. The index of refraction of the surround of the medium, not the surrounding medium, the glass. For lenses, you know, seeing lenses, here you go, seeing lenses. For seeing lenses, we have the same equation that relates the positions of the object and image with the focal distance. And the same equation that we use for the mirrors, right? That we use for the mirror that relates the positions of object and image with the focal distance. So let's go ahead and copy it there in the back. Shouldn't be difficult to remember that, right? Focal distance, 1 divided by the position of the object, plus 1 divided by the position of the image. In addition to the above equation, We also have a relation that relates an equation. We also have an equation that relates the focal length of the lens, its refractive index, and its radii of curvature. And it's going to be something like that, 1 divided by f, right? Going back into the equation. Here you go. Here's the refractive index of the lens. And minus 1. That can be proven. And it's proven in the last section right in here. What else? One R1. That's the lens maker equation. We call that minus 1 R2. Okay. We have exactly, when it comes to the magnification, we have exactly the same relation as well. Okay. So how exactly does this type of object refracts the light, right? It's just like the same way that it refracts a surface. It's the same way that light is refracted to an object, okay? Through those procedures that we did. Here you go. If the object is incident here, this is spot in the lens, on the lens. We have, at that point, we have a line that's tangent to the surface right in here. And the light is refracted inside the object. So it's bent towards the normal. So I'm going to exaggerate a little bit like that. And then refracted back, refracted out with respect, here you go, more or less like that. It's not going to be parallel because we have a different curvature here. Okay, it should be parallel if the two surfaces were parallel. Okay, the same thing happened on the other side, right? Since here you go, if the light is incident right here at the middle of the lens, at the middle of the lens, the angle of incidence is 0 degrees. So there is no refraction whatsoever. The light is slowed down, but there is no refraction whatsoever, right? So here you go. And that's because the normal incidence eventually is going to cross the other one. And if you have same light ray right here, it's going to be bent towards the normal as well, just like the other one did. I'm doing qualitatively, okay? And then it's bent away from the normal, but it's still, you know, that's qualitatively how it looks like, okay? So there are all sorts of surface that you can have. You can have double convex, double concave. Double convex lenses are represented by this double arrow is double arrow, right? The convex surface is represented by something like that. Okay, this line here indicates the direction of the surface, and those two lines indicates that the surface is concave. Concave, convex, two different lenses. What are here you go, here's the representation, right? How can we come up with the image of the object, right? That this type of lens forms. So we're going to start from scratch. Go too many stuff for you to understand, right? I'm going to start just with the lens. Let's go. Lens, go. I don't need that. The best way to understand, don't forget, is to practice that on your own in your paper there. Okay, let's put a little bit here. Okay, and then we go ahead, draw the axis. I call that the x-axis. We are going to in the next drawing, we are going to position the focal point of the lens and its other focal points. You go. I'm going to position this one right in here. Move it aside. In the next step, we position the image, the object. Let's say the object is located past the front focal point after F prime, right in here. All right. One light ray that you can use is the light ray that goes parallel to the axis of the lens. Right, so here you go. Lens axis, principal axis of the lens, the two focal points, one in front of the other. The actual, here you go, not the two focal points, but this is the actual focal point. This is just the image of the focal point in front of the lens. What is the focal point? Focal point is the point through which parallel rays are refracted towards, okay? All parallel rays are refracted towards. This distance here is lowercase f from here to here. Okay, put your object. We're doing that, the object in front of the lens first, and then here you go. Here's the first light ray. Right, here you go. Parallel to the axis of the lens. Here you go. Here you go. first light ray. Let's document that. Here you go. Light rays of a lens. Light rays of a lens. Okay, one parallel to the lens axis, refracts towards the focal point F. Okay. The next one passes through point F prime. And refracts parallel to the axis of the lens. Here you go. We have our first point of intersection right in here. So the image should be formed somewhere around here. Okay, notice that this distance here is 2 squares, right? Because the object is positioned at 2 squares as well. But we can also come up with a third light ray. The third light ray is the light ray that passes through the center of the lens. It suffers no refraction whatsoever. Here you go. And finally, we have this image that is formed. I'm going to put this image with a different color. Okay, right here. Let's not forget that we have the following parameters here. Let's make it a little bit thinner. Here you go. This parameter here is little p. Little p. Then we have this other parameter here. Little I. Right? According to the equations that we get, this one also is going to be H, right? And the other one is going to be H prime, the height. The H prime, the height of the image, the height of the image, the height of the object. There's no center of curvature here because actually we have 2 centers of curvature, right? In the case of the mirror, we have just 1 center of curvature, but in this case, we have 2 centers of curvature, so you cannot have a forced light ray. Okay, so here you go. Now we can start playing with this image. Here you go. If the object is a little bit further away, instead of 2F, the focal point, right? Here is, oh, and by the way, there is one more that I gotta put here. One more distance that I have to put here. Here you go. Here is gonna be F, lowercase f. lowercase f as well. In this specific case, P is equal to 2F. That's why the image is being formed at the same distance. So here you go. So let's come up with different conditions here, right? Here you go. If the image is a little bit further away, here you go. The object a little bit further away, the image is going to be formed elsewhere. Go. Let's see here, this one here, to have, and then we have this other one. Okay, this one here. Now let's see, did I do everything right? No, I didn't, right? Let's see what's going on here. Deflected towards the focal point, this one here. Let's see. I'm not getting the right, oh, that's why. Okay, this one should be like that. Okay, now we got it right, right? And now the image is being formed right here at this spot. And that's one type of image, right? As I approach the object to the lens, you go. Further away, closer, right? Playing the movie, right? That's something that we can do with that simulation that you saw yesterday. As we approach the focal point, you go, this one doesn't change anything, this one changes. You go. And this one. Let's see here. Okay, there's a mistake here. Here you go. Don't forget it passes through the focal point. Oh, by the way, see that sometimes you come along this type of problem, right? You don't draw the lens large enough, and then you get confused where this light ray is going to fall. So all you have to do is ensure that that the lens is a little bit larger. That's all you have to do. Imagine that the lens, has been extended. So it does that happen, and sometimes we end up a little bit confused, right? Because of that. So here go where this guy is going to intersect the other around here. If I did everything right, they should. Yeah, here you go. Oops. It didn't get there. Okay, let's see if everything is right. Here you go. Yeah, parallel 3 light rays. Now let's see the movie, right? Here you go. Here you go. Smallest, larger, larger. The image keeps on growing, right? And then in the next step, the object is positioned exactly at the focal point, a distance equal to the focal distance. This light ray doesn't change, but the other two changes. Here you go. Okay, at this point here, it's difficult to to say where this light ray is, how this light ray is going to pass, right? The focal point, maybe it would pass like that. But what we can see is that in this specific case, what we end up having is two parallel rays that emerge from the lens. Because those rays are parallel to each other, they don't intersect, right? And how can I prove that they are parallel to each other? We can prove they're parallel to each other by just observing that this distance here is the same as this distance, right? See, you have this and also this distance here is the same as this distance. Just look at this triangle, right? This triangle has this side that's equal to this side. This other triangle has this side here that's equal to this side. Consequently, those two sides here must be parallel to one another. That's when we form an improper image. Focal point. No image is formed whatsoever. Oh, okay, let me see here. I gotta fix some things here, right? This one is not 2F this anymore. And oh, there are lots of things here that I didn't fix. This one is going to be the position of the image. Let's see if you have the same problems in the other ones, right? You go. Yeah, position of the image. That's okay. That would be 2F, but not this one, right? This one here is not 2F. You go. Okay, approaching. At the focal point. It's not 2F. This one is just F. Improper image. H. What about another one? There you go. Closer now. Again, you go. Less than F. Should be less than F here. Here you go. This. Now, do you see those two light rays that are diverging each other, right? And then we in this we can have a third light ray, like in the others. Here you go. Those two light rays are diverging from one another. What about the third light ray? How is it going to look like? The third light ray that passes through the focal point, it looks like the following. It passes to the focal point, but the focal point is behind the object. Okay, at that spot, it refracts parallel to the axis. All right, and then what you do next? You extend this line backwards. All those lines, you extend them backwards. Just like this one. And if I did everything right, all these three lines should intersect at the same point. Okay. And what we form here now is an upright virtual image. Upright virtual image. Here you go. Here you go. Here's the principle of the magnifying glass, which is one of the optical instruments covered in the last section of this chapter. Okay. The closer the object gets to the lens surface, good. What happens to the image? Don't forget, go, let's get it. The larger the image becomes. Now it's not, doesn't even fit here in my slide, right? Doesn't even fit here in my slide. I'm not gonna do that because it's not fitting there. So here you go. What you see here is exactly that simulation that I showed to you yesterday. Closer, closer. Parallel light rays. And then we start to form a virtual image. Okay. So 3 light rays in this case. Let's write that down. Parallel to the lens axis, refract towards the focal point. Light ray parallel to the lens axis. Light ray, what else? Passing unrefracted through the center of the lens. And the third light ray passing through point F prime, refracts parallel to the axis. 3 light rays. And then you can verify everything here according to this equation. Now that's convergent lens, right? Convergent lens. Convergent or positive lens. And refracted like that. Okay, let's take a look at the negative lens now. Okay, here you go, negative lens. Right? So let's start from scratch. Just like before, let's start. Let's do what we did before, right? There you go. You start with the lens alone. You go. A little bit. Longer. In the next slide, we are going to have the axis of the lens. We label it X. X-axis. We mark the focal points in front and behind the lens. Just make it one square distance. Good. And then, okay, let's make this axis a little bit longer, right? We're going to need it. Here we go. And then we position our object at different spots. Here you go. I'm going to get this object here. Let's start at position that's far away, like that. Okay, those lenses are divergent lenses. Consequently, we should expect the light ray to diverge at the surface of the lens to refract away, right, from the normal of the lens, right in there. So here go with one important detail. When you extend the light ray, it passes through the focal point. Right, so I prefer to draw this light ray as though it's a dashed light ray. Here you go. To remind you that we are extending it, right? Here you go. Nope. Doesn't look like. Let's see another one. No, either. One more. What about this one? Okay, this one is better. Good. Another light ray is going to pass through the center of the lens. Just like the other one, the positive lens. And doesn't get refracted. If I did everything right for those two light rays, I already know where the image is being formed, right? The image is being formed right in here. And we finally have the last light ray. Okay, here you go. That's going, passing through the focal point. Go, this one here. Let me see here if I gonna be like that. Okay. Let's make sure I get it right. You go. Extended, but let's not forget a light ray that passes through the focal point is refracted parallel to the axis, right? And again, if I did everything right, and then you extend that refracted ray, what you end up having is this image. Let me see here if I got it right. Okay, this one here. 1, 2, 3. Yeah, that's right. Okay, 1. Let's see. 1. The red one is the 1. This one is the second one intersected in here, and this one is the third one. When you put too many of those lines, you may end up a little bit confused, right? So format shape. This one, no, it's not what I want. Yeah, I got decrease like that. So here we go. Okay, and now I gotta change to gray. Here you go, image formed. As we approach the object to the lens, this one doesn't change, but the other two does, right? Focal point. I put like that, so it's easier for me. Light rays refracted. This nope. Let's get it. Move it away. Here you go. Here you go. Dashed line. Because though it's a ghost, and we extend the light parallel. This one goes through the center, right? So here you go. We get this image right in here. Okay. Approach the object. Closer. Go. I did most of the work in the very first drawing, right? Here you go. You go. Path right in here. Whoa, whoa, whoa. Do-do-do-do. You go this one right in here. This one right in here. Huh. Look at it. What else? What else? This one, yeah, looks like they're intersecting at the same spot, right? This one, yeah. So move a little bit forward, right? And so on, right? You go, one more. What happens at the point of the focal point? Here you go. What happens at the focal point? At this spot, here you go. This one. Move a little bit like that. Here you go. They are all intersecting at almost the same spot, right? Here you go. Just like the convex mirror, you know, the image doesn't change much, right? It's going to be upwards and it's smaller. Okay, let's do one more. Closer. Okay. Go. We got this one here. Okay, so here you go. Our movie. 1, 2, 3, 4, 5. Right? That's what we have for lenses. Divergent lenses. Any questions about that? 909 already. Let's see, I'll keep this one for now. And let me take attendance and then we go for our break. Lecture, today is the 29th. Toby, are you there? Toby's in there, but he's not answering. Aaron, are you there?
Yeah, I'm here.
Okay, Musa, are you there? Musa? Yeah, I don't see Musa there in the list. Okay, it's coming.
Oh, Professor.
Yeah, who is that?
Toby.
Toby, yeah, okay. Okay. Musa, are you there? Yeah, good. Next, Zachary Blue.
I'm here.
Okay.
Present.
Thank you. Elena? Elena, I see Elena here. Okay, good. Thank you, Elena. Crystal? I don't see Crystal listed here. Brian Spino? Let me stop sharing the screen. Brian Spino not here. Next is Robert Faust. Thank you. Pedro Flores. Thank you. Next is Lawrence Flores.
Here, Prof.
Thank you. Daniel Freire. I don't see Daniel here. Amalia Gale.
Here, Professor.
Tiffany Wong. Good. Thank you, Olivia Kruger. Next is Daniel Yang. I see. Are you there, Daniel Yang? I see you listed, but it looks like he's away from his computer. Sarina, are you there? Sarina, I see Sarina here, but I don't hear anything from her. We're gonna get a star for now. Anthony Lopez. Next is Chuck Lu. Thank you. David Maes. Good. Next is Ryan McNeil. Thank you, Ryan. Alexis Nigret.
Here.
Thank you, Alexis. Daniel Nwagbo.
Yeah.
Thank you. David Nwagbo.
Yeah.
One more, Claire Ottinger. Is Claire here? Okay, I see Claire listed here, but I don't hear anything from her. Next, Jennifer Hamides. Good. Noah Raymond.
Here, Professor.
Thank you. George Risk. Thank you. Shah Safi. Okay, good. Thank you, Shah. Natalie Santiago.
Here.
Thank you. Nathan Silva. Next is Darnice. Let's see, Darnice. I see her here. Okay, thank you, Darnice. Next is Kenny Villagomez.
No, I'm here, Professor.
Okay, thank you. Nolan Williams. Next is Meng Shu. I think I saw Meng Shu here. Yeah, gonna get Meng Shu's gonna get a star. I can't hear. I don't hear from him. It's Olivia Song. Are you there, Olivia Song? I don't see her here. Okay, 27. Yeah. Okay, good. So let's go for our break. Is 9:15 right now. So break till 9:30 a.m. Okay. So I see you in 15 minutes. Images, right? Here we go. Let's see. Solution menu. No, it's not what I wanted. Let's see this one. Yeah, this one here. Optical instruments, right? So here you go. We already did, there are some optical instruments out there, and you can use lenses and mirrors. To build those optical instruments. Okay, one of the optical instruments is the human eye, which uses a lens. It behaves like a lens. Okay, and it projects an image in your retina in the same way that a regular lens projects an image into a screen. Okay, and we talked about the magnifying lens. Okay, so let's take a look at the magnifying lens again. The magnifying lens works by positioning, works with a convex lens, with a positive lens. Here you go. That's how a magnifying lens works. Okay, you position an object between the focal point and the lens, and you look at this objects from the other side. Okay, the image is going to be virtual. Everybody's familiar with that, right? You get a lens to increase the size, to look at details of an object. But the key here is to put the object between the focal point and the lens itself. So what you end up seeing is a magnified version of the object. It's a magnified image of the object. Okay, so what is the magnification of the object? It's given by that formula that we saw before. Okay, it's Okay, is another way. Here you go. It's he gave the magnification in terms of the angle theta, right? But you can also get the magnification, he go, in terms of the position of the image and the position of the object as well. Here go, let's see. Which is that ratio that you saw before. I divided by P, okay? Here you go, I divided by P. Okay, when the image is a virtual image, this value here is negative, and the negative sign cancels out. Okay, so there is this the magnifying glass. There is the compound microscope. I want you to look at that. Okay, here you go, the compounded microscope. You have an object right in here. Okay, how is the magnifying compound microscope works? It has an objective, and then you have an eyepiece, two lenses. Okay, the object, you put an objective, right? And then you put the object in front of the objective, the first lens. Okay, and this object projects a real image of the object somewhere around here. Okay, here you go. Light rays parallel to the axis, focused into this point here. Okay. And then what happens? You know, the eyepiece ends up imaging this real image. So this real image, you know, the eyepiece, you know, ends up working like a magnifying glass for this real image. And a new image, a virtual image, is produced much further away. Okay, giving you a magnified image. That's one. So that we're combining, right, different lenses. In this case, two different lenses. Refracting telescope, something like that Galileo Galilei invented. Okay, we have, just like the microscope, you have an objective and you have an eyepiece. In the case of, in both cases, both for the compounded microscope and the telescope, the objective has a focal length greater than the eyepiece. An object that's very far away, you know, passes through the objective and produces a real image at this spot. Okay, nearby the focal point of the eyepiece. Okay, and the image I prime is formed further away. Okay, so here we go. That's another device. Man, that's optical neuroimaging. Let's read about that. Here you go. Have you ever heard of functional near infrared spectroscopy? Okay. Okay, that's something that that was invented to find out how the brain works. Okay, you use the infrared light to probe the blood in your brain. The blood. Okay, so here you go. A person wears a close-fitting cap with LEDs emitting the near-infrared range. Okay, and the light can penetrate the skull up to a certain point, like 1 inch. The skull is transparent to this type of wavelengths. Okay, and there in the brain, you just have a hemoglobin that can be probed with these wavelengths of light. Okay, the light is scattered and absorbed by the hemoglobin can be detected with a photodiode. Okay, depending how oxygenated the hemoglobin is. So what do? They use this device. Take a look at this cap. You know, it's like a thinking cap. You will have different colors here. One of them is you know, some of them is LEDs, okay, light emitting diodes. Let's say the blue ones are light emitting diodes, let's say, okay, and the red ones is the photodiodes. So what's happening here? You have an LED that's emitting in the near infrared. The near infrared light penetrates the skull. Okay, remember, it's near infrared light, it's not visible light, right? Near visible light cannot penetrate the skull, but it penetrates only up to a certain thickness. I know people who works with something like that. And once it penetrates like 1-2 inches into the brain, that light is absorbed and scattered. And that scattered light is picked up by the photodetectors, these red devices that you see here, a bunch of those in this cap. Okay. And we can map the behavior of the brain depending on what you're doing. You're gonna get a different signal. Okay. What he says here, researchers are now using the infrared spectroscopy to map which parts of the brain are activated by which activities. So we can look inside the brain in a non-invasive, inexpensive fashion, just like electroencephalograms, right? And it's also very, very portable. And it can be fit anywhere. It can be used anywhere, right? Because the equipment is very portable. It's just a little cap. That's the headgear. And so you can do optical neuroimaging. There is software out there that are available publicly that you can use to process the image that you get from devices like that. Okay? Here are the proofs that for the equations that we got. I want you to look at that so you can understand how you got. You don't need to do this one because we skipped this section, but for the others, okay, for the other formulas, yeah, you have to. Okay, so here's the review and summary. And what we're going to do now, we're done with this chapter 34. What you're going to do now, let's take a look at the syllabus. We go. Chapter 35, we're going to start interference. Okay, and later on, you're going to have the speed of the sound virtual experiment. That interference of light, you know, that doesn't show up in the exam 2. Exam 2 is just those 3 chapters, part of chapter 17, chapter 33, and 34. Let's take a look at interference here. Light as a wave, okay. And some nice, colors that we see, for instance, the butterfly is due to the phenomenon of optical interference. Okay, so what are you doing here? Here you go. Let's go to my notes here, right? In this last chapter, we treated light as though as it behaves as a particle. Okay, in this case, light was treated in this case, the path of the light should be similar to that of a particle, traveling in straight lines. But light also behaves as a wave. Okay, in the case of a wave, light does not necessarily travels in a straight line. Okay. So under certain conditions that we will discuss, under certain special conditions, that's how light behaves, like a wave. In this part, this thing is also called wave optics. Let's take a look here, and here we go. And we, let's see how he called that. He called interference, right? But we also call this type of chapter wave optics. Okay. So let's take a look at the equation for the index of refraction, right? Let's remember, we defined the refractive index. Remember how we have defined the refractive index, right? We define the refractive index of a given object as the speed of the light in vacuum divided by the speed of the light in the medium itself. The refractive index is defined, relative to a medium, right? The refractive index is defined relative to a medium, and this medium is the vacuum itself, and it's defined in terms of the speed of the light, of the vacuum in the vacuum, and the speed of light in the medium itself. But this velocity can be rewritten in a different way as well. Remember the relationship for any wave, okay? The relationship, the speed of a given wave can be written down as the wavelengths of the wave in that medium times its frequency in that medium as well. When I put naught here, let's put V for vacuum, right? V for vacuum. So that's what the speed of the light in vacuum is all about. Can be written down in terms of the wavelengths, right? And the frequency. Well, a more intuitive equation can be written down not in terms of the frequency, but in terms of the period of the wave. Remember that? Here you go. And the inverse of the period of the wave is the frequency. You can do the same here for your medium. Let's see, let's keep it according to the wavelength of light in a medium. Yeah, okay, let's keep it according to the notation of the book, okay? So instead of lambda of vacuum, let's just put lambda itself. So we have the same notation that the book has. Here you go. And we do the same here for the velocity of the light in the medium. And following the notation from the book, we're going to do wavelengths of the light in the medium as being lambda n, okay? N is to remind you of the index of refraction of the medium divided by the period of oscillation of the wave as well. Here, writing that in terms of the frequency, we here write like that. Well, we can do something else. Take a look at this equation, okay? Think in terms of your source of light, okay? Source of electromagnetic waves. How can you picture that? Let me show you here. Oh, not this one. You have the wavelength and you have the frequency, right? So here you go. Think in terms of your wave, right? Your wave is generated by an oscillating source, okay? And this oscillating source can be very far away from the medium. Remember that? So that oscillating source generates a wave that propagates from the source itself, okay? And then this wave may propagate through one medium and may, at a certain point, get into a second medium, just like we had. See here, just like, oh, here you go, just like we have in the case of another dielectric. Okay, so here you go, what we have? We have the light coming from a source that's oscillating very far away. This source is oscillating, at a given point here in space, generating a wave that propagates from the source through the space until, let's say, a second medium. And when it gets to the interface between those two media, let's say vacuum and glass, this wave, this light wave, can reflect and can refract, okay? Now think about the frequency of the light in the medium itself, okay? I'm gonna make a drawing here for the source of the electromagnetic wave oscillating somewhere. Here we go. Here's the source, and I'm going to denote it by two arrows, that's oscillating back and forth, source. And then this source is generating this strain of waves. Okay. What you have to know about that is that the frequency of oscillation of this wave is going to be the same whether it's outside this medium and whether it's inside this medium, because the source that's oscillating is outside the second medium, okay? Because of that, we can write down that the frequency of the wave inside this medium of refractive index n is going to be equal to the frequency of the wave outside the medium itself, because that's where the source is located. Having said that, we find, this F cancels this F. And we have that the refractive index of the medium is inversely proportional to the wavelengths in the medium. Here's the wavelengths in vacuum. You remember that we saw that behavior of dispersion, right? That the index of refraction depends on the inverse of the wavelengths. So that's what that behavior is coming from, okay? The wavelengths in the vacuum of a given color doesn't change. But when the same light penetrates a different medium, you're going to have a different wavelengths. You're going to measure a different wavelengths for the same light. Okay, so here you go. You can write that. The wavelengths decreases with the refractive index. That's what you have at this equation right here. Lambda with the wavelengths in the vacuum. Here you go. Lambda in the above equation. Here you go. In the above equation, lambda is wavelength of the light in vacuum. Note that when the wave propagates from vacuum to a second medium, its wavelengths changes, but not its frequency. Okay? That's because the source generating the wave is located outside the medium, and its frequency of oscillation is not affected by the medium that is far away. Not affected because the source of oscillation is not in the medium itself. Since the velocity of the light changes in a medium of different index of refraction, then the wavelengths of the wave must change. Okay? In other words, frequency, in other words, the frequency of oscillation of the wave is the same whether irrespective to the medium of propagation the wave is found. Okay, that's the first piece of information that you must know about this phenomenon. Okay, so here you go. So light behaves like a wave. And how can you picture light? You can picture light as being waves, as being like a wave front, okay? Made of several little, spherical waves that are propagating in tandem with each other at the speed of the light. Here one position of the front, here's another position of the front as time goes by. For the case of planar waves, right, they're represented by those lines parallel to one another. Here is the peak of the wave, right? The distance here is the wavelengths. And now that we know that the wavelengths change, once the wavelengths decrease, right? When you go from one medium of lower refractive index to higher refractive index. So now we can illustrate this wave inside the medium as those wave fronts inside the medium as being closer, okay? The wavelengths here is shorter than the wavelengths here. Here would be the wavelengths in vacuum. Let's see how I'm gonna illustrate that. I'm gonna do a little bit further away so it doesn't stay too bunched up, right? Here you go, better this way. So you can picture it better. That's how you should picture those waves. Okay, here is one of the front, and when it gets inside the medium, the wavelengths decrease and the path of the wave is bent inside the material. How can you picture that? What would be a good analogy for this type of behavior, right? If you took the lower level physics, they have a very good analogy for this type of behavior. It's the case of the a car. You know, think of the light as being a vehicle that's, you know, that's traveling along this path. Let me take away those guys here. Analogy. So here you go. Here's the axle of the car. Okay, so here you go. Analogy. Mechanical analogy with the wave. Here you go. Mechanical analogy of refraction. Okay, so here you go. You have the axle of the car that's following this straight path. And now here goes the regular pavement. I'm gonna put the wheels of the car right in here. Let's proof down. Because the pavement has better track, and here you go, we have a pavement here and we have a grass on this spot, right? Because the pavement has better traction, so this car is gonna travel faster in the pavement. However, when it is about to enter the grass region, okay, something happens. The grass doesn't have as much traction as the regular pavement, okay? And because it doesn't have as much traction, this wheel here is going to slow down compared to the other wheel, okay? And because here you go, this outer wheel is spend longer time here in this region with traction, okay? And when this wheel enters here, this grass, what's gonna happen? It's going to slow down a little bit compared to this one, and this one is gonna rotate faster, right? Think about this other wheel traveling faster than the other, it's going to result in something like that, because it has more traction than the other. Here you go. What was initially something like that? Right, here you go, the wheel moving, right? When it gets here, this wheel here is going to move faster than this other one, and the tendency of this car would be to rotate about in this direction, okay? That's the analogous, the mechanical analogous of optical refraction. Okay, I'm gonna even rotate a little bit more. Here you go. Because this wheel here speeds up compared to this one. Okay. Okay, having said that, we can start to think about wave optics effects. Okay, so here you go. Here again, the same discussion that I made for the car, right? Here you go, wavelengths outside the glass, the way we have wavelengths lambda 1. Inside the glass, we have wavelengths lambda 2. That ends up to being shorter than the wavelengths lambda 1. Okay, remember that. So inside a medium of higher refractive index, that's an important result, right? Higher refractive index, the wavelengths of the light becomes shorter. Okay. Becomes shorter because the speed of the light is less. Frequency doesn't change. Shorter compared to the previous medium. Must have this picture in mind. Okay. So let's skip that, and here you go. It's a very good. Now here we have a monochromatic ray, right? This monochromatic ray is incident at this interface between medium A, media A, and medium B. And the light is refracting away from the normal. What can you tell me about the refractive index, the relative refractive index of those two medium, right? Think about that. And then from B to C, the light refracts towards the normal. And from C to A, and from C to A again, it refracts towards the normal again. Okay. So what's going to be the refractive index and the speed of the light in those different media? Think about that. That's a very nice problem to keep in mind. Okay, so because light is moving away from the normal, it means that refractive index of B is less than refractive index of A, right? So let's write it down here. I'm going to shrink this. No. Okay, checkpoint. Checkpoint 35.1.1. 35.1.1. Okay. So here you go. What we know that in sub A is going to be greater than N sub B. Which implies what? This implies that the velocity in medium B, in medium A, is gonna be less than the velocity in medium B, right? There you go. What about B and C? Okay. Okay, in the case of B and C, light is being refracted towards the normal. And what does it mean? It means the refractive index of medium C is greater than the refractive index of medium B. What does it mean? It means the velocity of light in C is less than the velocity of light in B. Make sense? So we go. And then from C to A, we're back to medium A. So light is going towards the normal. What does it mean? It means the refractive index of medium A is greater than the refractive index of medium C. So, which implies that velocity of medium A is less than velocity of medium C. Make sense, right? Lower refractive index, higher refractive index, even higher refractive index. Here you go. Lower refractive index here, higher refractive index with respect to this one, higher refractive index with respect to this one. The higher the refractive index, the lower the speed, the slower the speed of the wave. Okay. Here you go. We did this equation here. I derived this equation for you. The frequency doesn't change, no matter where the medium that the wave is propagating, right? And then we have the case of a phase difference. Since here you go. Since light behaves a wave, it also has a phase. And this phase may change when light, and this phase change as it propagates through space, okay? And when it is reflected at interfaces. It's the same principle that we saw with the wave in the string. Okay, let's see if I can get to, here we go, not this one. Let me get, oh yeah, here you go. That's a good analogy here, okay? Here you go. Whenever you have a mechanical wave propagating a string, if the end of the string is loose, we discussed that before, right? There is no change in the phase of the wave, right? Something similar like that happens to light in different medium of refraction. Here we have a reflection of the wave, right? However, if the end of the string is fixed, like in this case, it's propagating to the left, the phase of the wave is changed by 180 degrees. The reflection upon reflection at this point. Again, we have an analogous for light, okay? And what is this analogous? Okay. In the light analogous, Go. I want to put it here in this. How is the phase of light wave affected upon reflection, right? That's what you have to ask yourself. Okay. Well, it depends on the relative refractive index, relative refractive index of the material. Okay. Mechanical analogous. Mechanical analogous. Okay. Analogous. So I'm going to make a table here for you. Insert 1, 2, and 3. Here you go. Mechanical, analogous, light wave. Okay. Let's see, fixed. Let's do this wave. This way here we go. Light wave. Instead of mechanical analogous, let's put mechanical wave. Like a wave in a string. Fixed and okay. Fixed and what does it? What's the analogous for the light wave? Okay, so here we go. That's let's go back here. Well, when the light goes from a medium of lower to higher refractive index, okay? And we are talking about in terms of reflection, okay? Let's see here, let's go reflection. We need one more. Let's see. Let's put this one here. Wave upon reflection. Fixed and 180 degrees. Let's see. I gotta come up with a better table here. Here you go. Let's do it without the table first, right? Reflection of a wave. Mechanical wave. Mechanical wave, here you go. Fixed and phase change by 180 degrees. We call that a pi, right? Pi phase shift. Pi phase shift. Go. Symbol. Okay. Not fixed, but free. And right? Phase change by 0 degrees upon reflection. Upon reflection, okay, of a wave. So we have the same analogous for a light wave. Okay, phase, the fixed end should be the case in which light propagates from lower to higher refractive index. There's a phase change of the light by 180 degrees, or pi phase shift. Okay, and the other analogous is the case when you have propagation of the wave from higher to lower refractive index. Let's see if we can put that in a table. Yeah, we can put that in a table. Here you go. We're going to do the table like that. Tables are much reflection, wave reflection, right? Like that. Mechanical wave, light wave. Phase shift, here you go, 180 degrees. Fixed and lower to higher refractive index. Let's do this way, here you go. Lower to higher refractive index, 0 degrees. Free end, higher to lower refractive index. Okay, so here you go. I'm going to put this way, N1 less than N2, right? N1 is the first medium, N2 is the second medium. And then we have the opposite. N2 less than N1. Keep that in mind. Okay. Let's see how you can picture the analogous of the wave. How can you picture here the analogous? Let's see here. We're going to, okay, should be right here at this spot, right? So upon reflection, let's see if I can illustrate that nicely. The spacing will remain the same upon reflection, right? It's just the phase that has changed. Let's see, let me copy and paste. I'm going to delete this one here. Here you go. All right, so here you go. Here's the interface. I'm going to put a little bit further away. This wave front. Here you go. Huh. Yeah. The wave must be, you know what? I'm going to do it differently. Here you go. There's a better way of doing that. I'm going to get this guy here. And now all I have to do is to copy each of the front edge, each of those edges here, this rectangle represent a wave, right? Here you go. Now, here you go. Better. And the lengths, you know, the thickness of this rectangle is the wavelengths of the wave. Okay, here you go. Now, what about the phase? Here you go. Here is the source of the wave, right? maximum amplitude here, maximum amplitude here, maximum amplitude here. Okay, that's a very good illustration of how your wave, and I can even write it down, the wavelengths for you. Here you go. Symbol. Here you go. Wavelengths. Here's source. I'm gonna label that source. So it's not, so you don't confuse this one with the other one. I'm gonna make even thicker. Here you go, source, S for source. Here you go. Oscillating back and forth, producing this wave. That's what the source is doing, okay? That's what the source is doing. Move a little bit, here you go. Crest of the wave, crest of the wave, crest of the wave, right? And here in between, you have the valley. And at this point, you have a zero amplitude and zero amplitude, okay? That's how we picture that. Okay, so refractive index here of this medium, let's say, is N1. N1. Oops, nope. Go. Subscript. And refractive index of this other medium is N2. Which is greater than N1. Okay, so what happens upon reflection? Okay, upon reflection, this wave here, I'm going to go, it's gonna be like that, right? But then we also have a phase, a change in the phase of this wave. What does it mean we have a change in the phase of the wave? Okay, it means that at the very point of reflection, we have a phase change that's 180 degrees, okay? So let's put this way here, you go. See that? This point here, the phase changed by 180 degrees. So what was a peak here became a straw here, a valley here, okay? And the peak occurs at a half wavelength from the reflection point, okay? Another way to illustrate that would be what? Another way to illustrate that would be to illustrate like that, right? At the point of reflection, you have this straw right here, okay? I like this one better. I prefer this one better. It's not the wavelength, it's not the wavelength became shorter. No, no, no. I'm just representing the valley of the wave. Okay, so here you go. Next, that's how you propagate. That's how we should picture. Okay, that's because N2 is greater than N1. Okay. Now, what if N2 is less than N1? It's just like the other situation, right? That you saw. What if N2 is less than N1? Right? So we do not have the shift in the wave. This shift in the wavelength. In the phase, this shift in the phase. No change in the phase. That's between two dielectric media. Okay? That's between two dielectric media. But what about a mirror? In the case of a mirror, okay? Here you go. Mechanical wave, phase shift 180 degrees, right? Lower to higher refractive index, higher to lower refractive index. Higher. Let me see how I'm gonna do that. You know, I'm gonna do like N1 means the first medium, okay? Let's put it this way. N1 means, you know, let's leave this way. Yeah, let's leave this way. But also, if you have a mirror, in the case of a mirror, you also have a 180 degrees shift. Okay, mirror surface. In those two cases, you have a phase shift of 180 degrees. 1030. Any questions? So I've been doing that for 1 hour already. Let me save that. This material is not going to show up in the exam tomorrow, okay? Keep that in mind. And let's have our break now. Break to 10:47 a.m., 15 minutes. And then we can continue with this material. Okay? See you shortly. I'm going to start. So let's just summarize what we have done so far, right? So here you go. 1, I stated, that light behaves both as a particle and as a wave. And there is evidence for both, experimental evidence for both of them, okay? Okay, what else you have to know? The wavelengths of light changes when it propagates from one medium to another of different refractive indices. Okay, that leads to these different distances between the peaks of the wave, right? What else did I mention to you? Okay, because light behaves as a wave, okay, it has amplitude, right? Wavelengths, and just like which one's the other one? And frequency. And frequency, right? Those are the 3 main components of the wave. That should be the second one right in here. Okay, and that leads also to a phase difference, and that also leads to phase, right? Because the wave has a light is a wave, you end up having a phase as well. Okay, every wave has a phase, and in the case of light, its phase may change upon reflection, depending on the depending on the surface. Okay. Something else that that you have to know, right? Also, because light is a wave, it can also undergo interference with another light wave, right? Just like we did in the previous in the chapter of waves 1 and 2. So what I want to talk about right now is a historical experiment that demonstrates the fact that light is a wave. Okay, there is a very important experiment called the Young's experiment by Thomas Young. Let's take a look at this guy in the internet. Here you go. Thomas Young. Double slit experiment. Okay, so what this guy did? This guy, Thomas Young, he managed to generate 2 light waves and observe interference in a faraway screen. Okay, so I like Wikipedia, so let's take a quick look at his biography here. Okay, he was born 1773, died 1829. Let's take a look at Newton's. Isaac Newton. And when he died, when he was born, Isaac Newton. Here you go. Not just a mathematician, he was also a physicist, right? Here you go. Now, he was born in 1642, died in 1726. So take a look. He was born 1773. So there was an overlap between Thomas Young and Isaac Newton, right? Newton was an Englishman, and what about Young? He was also an Englishman. So here, what we want to talk about is his wave theory of light. He was the guy that introduced the wave theory of light. And he did this famous Young interference experiment, an experiment that we do in the lab, a real experiment that you do in the lab. So what did he do? He considered light to be made of a wave like this one. Let me see if I have an illustration for that. Okay, current. Yeah. Oh yeah, here you go. Here I have an illustration of the experiment. Okay. That's something that we can easily do today with a laser beam. At that time, Thomas Young didn't have a laser beam, so he had to do in different ways. Okay. So how does it work? How this experiment works? You get 2 slits, okay? Can be 2 pinholes. What I mean by 2 slits? I mean 2 pinholes, okay? And we shine this region of 2 pinholes. They're separated by a given distance d, okay? So let's start with the movie, right? We start. I'm gonna, too busy. This drawing is too busy, so it's difficult to understand what's going on, right? So let me eliminate as much as I can so you can understand how this whole thing works. Okay, I'm going to go. Two slits separated by a distance d. I'm going to put it right in here. And I'm going to show you a video as well, so you can understand better. Here you go. Two slits. Distance d. We have those things there in the lab at LA Harbor. A bunch of those. And I always do a demonstration for my students in the classroom so they can understand how this whole thing works, right? Just doing, So and what else do? We go ahead and shine light here in those two slits. I'm going to erase those two guys. So here you go. And we get a laser beam, and here's the laser beam. Shine light. I don't like this color, so here you go. I'm gonna put this color here. Laser beam. Laser beam. All right, here you go. And I'm gonna two slits separated by distance d, lowercase d. And in the other one, two slits. Okay. Two slits, right? Separated by distance d, and we shine a laser beam. Shine a laser beam in the slits. What else do we need for this experiment? We need a screen far away from the slits. Okay, screen at distance, screen far away from the slits. Okay, and we say that this screen is a distance L. And this distance L must be much larger than the separation of the slits. Go, my line here should be horizontal. L much greater. And then, and then we shine a laser beam in the slits, okay? I can even put some arrows here to denote that this is a light propagating. Here you go. A bunch of lights here, go. Bunch of arrows denoting the propagation of the laser beam and its incident on this slit. you go. Okay. Now, what's gonna happen here? Well, the following is going to happen. Some of the light is going to propagate from one of the slits and is going to be incident there at the screen that you saw. Let me eliminate that. No. Beam light wave propagating from the upper slit. From the upper slit to the screen. Grid line, go. Okay, from this spot to this spot, okay? And then you're going to have light wave propagating from the other slit also to the screen right in here. If light is a wave, right, you can picture the wave right in here in this line, or you can use that representation that you saw before too, right? Here you go. The representation that I showed to you as well, showing the straw, the peaks and the straws, right? So here you go. That's one of the wave. Let me make it red. Red. No, I gotta put it black here so you can see the wavelengths propagating from here, right? Here you go. Right? Peak, 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 wavelength, 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 right? Here you go. Let me put everything here. So we have this wave propagating from both slits. And when it reaches the screen, they are going to interfere with each other. A little bit off, right? So yeah, I gotta, let me see if I can rotate them so I can get the right. Here you go. More or less, yeah, I cannot get better than that. Okay, so here you go, ungroup. They're not exactly at the right angle, but you get the idea, right? Okay, if I put my screen a little bit further away, I can get the peak of this red wave there, exactly at this screen. Okay, so here you go. Now this wave is kind of in phase with this screen, right? It started with maximum amplitude here, and I adjusted the screen so it ends with the amplitude there as well, right? And now I'm going to show you the blue wave. The blue wave, by the way, is a monochromatic light source, okay? So they have the same, because it's a monochromatic light source, they have the same wavelengths. They have the same wavelengths. Their lengths, their width, right, is exactly the same. So let's see if I can get it. No, it doesn't work like that. I'll have to look this one here. Here you go. Put this one right in here. A little bit off, right? Here you go. Hopefully it's good. It's good enough. Now, here you go. I'm gonna put them in blue colors. So to distinguish one wave from the other. Good. Okay, so I guess I have it. It's a little bit off. Let's see if I can get it. Rotating the right angle. You know what? I'm going to adjust this guy. It's easier to adjust this guy than to adjust those wavelengths, right? And now I can place everything right in here. Again, let's paint it with a different color. Fill with a different. Here you go. Yep. It doesn't mean that we have a different wavelength. No, no, no. It just means that I want to distinguish one beam from another, right? The wavelength is the same. So you can see here, you know, from this crude illustration, right? It's not exact, but we can see that those light waves have almost the same phase there at the screen. Okay, they arrive almost at the same phase in the screen. So I can tell you that at this point, there will be constructive interference of those two light beams. Make sense? That's how the two-slit experiment works, okay? At certain points, you're going to have constructive interference. At other points, you're going to have destructive interference of the light wave. Okay, and now I'm going just to denote this light waves as light rays. Okay, I drew this thing here just so you have an idea of the waves propagating there to the screen. Okay, here you go. It's a little bit shorter. Here you go. They're interfering right in here. Right, in the next drawing, what do we have here? Okay, in the next drawing. So what's happening here? We have a small slit and the light is propagating as though in a spherical sense, right? There's a point of light here expanding as though they are ripples in the water. That's the good analogy that we have. So what else do we need to know? We need to know the angle and the distance of this, that this light ray moves until it gets to the screen. Okay, I want to make sure this guy is okay. So here you go, this horizontal line, and okay, and I'm going to get this one and paste that here as well. Here you go. Angle that this slit, that this light ray makes with the horizontal. We can come up with the other one as well. This one I call D1. Okay. If this one, oh, I'm gonna put this here. Next one, what else? Okay, I'm going to come up with a line that goes from the center of the two slits to the screen as well. Here we go. Okay, those are all parallel lines, horizontal, right? 1, 2, 3 horizontal lines. We have an angle for this other light ray. Strictly speaking, those angles are not the same, strictly speaking, but because the distance L is much greater compared to this distance D. Remember, it's not in scale, right? This drawing is not in scale. We can come up with this approximation that this angle here is the same as this angle, okay? Okay, so, and what we're gonna do here, we're gonna come up with a very simple equation that's gonna give us a relation for the phases of those two beams along this screen, right? If the phase is 0 degrees, you're going to have a very bright image. If the phase difference between them is 180 degrees, you're gonna have a dark spot in there. Let me show you exactly how it works in real life, okay? We have here a Thomas Young double slit experiment. Here you go. Here you go. That's the drawing that I made, similar.
Hello.
More
My
detail,
name
of
is Bill
course.
Harrington, and I'm a graduate student at the Massachusetts Institute of Technology. We're in the Course 6 Modern Optics Project Laboratory, and this is Young's double slit experiment, an important experiment from around 1800. We have a laser shining light onto a pair of identical slits. These are rectangular.
Here you go. Here are the slits. We have those slits there at LA Harbor. Different distances, different separations, okay? And we have a laser here in the back here. The slit should be this one right here. And see the screen? Notice that the separation of the slit is very small compared to the distance. Okay? L is much greater than D.
Transparency. After shining through the slits, the light propagates some distance to a screen where we can observe the resulting pattern. We have a webcam set up so that you can see what's happening.
Okay, here you go. Here is the result of the pattern there in the screen. Okay.
Right now, we've blocked one of the two slits.
So do you see what he said? He blocked one of the two slits, and you're seeing right now, you're seeing this smudge there in the screen, okay? It's not an interference pattern yet because he blocked one of the slits.
The light is propagating through a single slit, and this is the pattern that results. Let's see what happens when we open the second slit.
Yeah, watch this drawing of this this picture here when he exposed the second slit, right, to the light. Here you go. We have two slits now, and take a look here at the pattern that's observed. This thing is you know, can be demonstrated easily in the classroom. You see bright spots here and dark spots here, right? Bright, we call it fringes, bright fringes and dark fringes, bright fringes and dark fringes. That's exactly what Thomas Young observed back at his time. He didn't have lasers, so he had to do it in a different way, okay?
The pattern changes significantly. You should be asking yourself, why has the pattern?
So why is that? That's because you have interference of light. Here you have constructive interference. The light of one slit is in phase with the light of the other coming from the other slit. And here you have destructive pattern. The light of one slit is out of phase by 180 degrees or half a wavelength with respect with the light from the other slit, okay?
Change. And why is this experiment important? The answers to those two questions are related. To understand why this experiment is important and what we are observing, you have to go back to the days of Sir Isaac Newton.
Okay, so why this experiment is important? That's historical experiment. It was the first time that someone demonstrated the wave nature of light. Okay, until then, people believed that light behaved just like particles because of the influence of Sir Isaac Newton.
At that time, people were debating the basic nature of light.
Here you
One
go.
group of people held that light was a particle traveling like a projectile from a source to an observer. Another group of people held that light propagated more like a wave, sort of like the waves you see moving along the surface of a body of water.
Well, the reality is that light behaves in both ways. Okay, both as a particle and both as a wave. It just depends on the scale that you're talking about. What's the dimension that you're talking about, okay?
Based on his own experiments and extensive observations, Sir Isaac Newton decided that light was most like a particle. Newton was quite brilliant and advanced science in a number of fields, so for many people, because Newton says so, was solid evidence that light was a particle, and Newton's corpuscular theory of light was widely accepted. About 70 years after Newton's death, another scientist, Thomas Young, was working with light, and he came to believe that light behaved like a wave. Young's double slit experiment attempts to address the nature of light by looking at what happens when light.
The same drawing that I made, right? The two slits and light being incident in those two slits.
Light passes through a pair of slits. If light behaved like a particle, for the double slit experiment, we would expect to see two overlapping copies of the single slit pattern. This does not match our own observations. On the other hand, if light behaves like a wave, we expect to see the two waves interfere.
Okay, so here you go. So we have the front of the wave, right, of one slit, the front of the wave of the other slit. When those two fronts intersect right in here, you have constructive interference. See that? Constructive interference here, 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 and so on. Destructive interference is, somewhere here in between. Somewhere here in between those two yellow lines. Okay, and the screen, can be placed here. So you see that the
Adding together
pattern
in some direction
of bright and dark fringes.
and canceling each other in others.
Yeah, let's take a look where it cancels. Here you go.
Together in some directions and cancel.
Here you go. That's where it cancels at this spot. Destructive interference. Yellow constructive. Okay, at the very center of the screen, we have a constructive interference, and then you have maximums above and below. Okay, we can derive the position of those fringes.
If we make some assumptions about
There
how
you go.
light propagates.
We're going to do that right now. Let's switch back to my drawing right in here. Okay, so here you go. Here the light beam from one slit, the light beam from the other slit. Okay, what you have to know next is that, we can come up with an approximation to simplify our equations. Because this distance here is much longer than the separation of the slits, I told you that those angles here, they are approximately equal. Because those angles are approximately equal, those two lines, they are almost parallel to one another. Okay. So let's see. I'm gonna document there in my notes. Okay. So here you go. Thomas Young experiment. The Young experiment consists of two slits, a screen, and very important, a monochromatic and coherent light source. Light source must be both monochromatic and coherent. Lasers are just like that. Okay. So the light from the same light source passes simultaneously through each slit, right? Okay, then experiment to the slit. Here you go. I'm going to put that separated by a distance d. I screen located at a distance L much greater than d, and a monochromatic and coherent light of non-wavelengths, okay? Non-wavelengths. The light from the same source passes simultaneously through each slit. Depending on the position along the screen, the light pass from one slit will the path length, let's put the path length of the light, right, from one slit will be different from the path length from the other slit. Okay, D1 is going to be different from D2. Here you go. D1 here is different from D2. If it is right here at the center, right, then the path length, the distance covered by each light beam is going to be the same. And because the light source is in phase with each other, because the light here, okay, I'm going to erase that. Because the light here starts in phase with each other, what you end up having here at this spot, in the middle spot, is going to be a bright fringe. Okay, D1 and D2. In this case, D1 is equal to D2. You go. In this specific case, the lights are in phase, and you have a constructive interference, a bright spot right here. Okay, bright spot at the middle of the screen. Light waves are in phase. Not the same cannot be said at other positions, right? So let's predict where is going to be a bright spot, where is going to be a dark spot. What do? We go. We are going to do a simple approximation to simplify our calculation, okay? So here you go. Because those angles here are approximately equal, the path length, the line connecting this slit to this spot here in the screen is going to be almost parallel to the other one, okay? Here you go. And because of that, we can state that there will be, you know, the difference between D1 and D2 is going to be this small lanes that you see right in here, okay? So what do? We draw a line that's perpendicular to this one because those two angle theta are almost similar. Let me erase this one. I think there's too much, right? Go. Those two angles are going to be almost the same. If those two angles are almost the same, those two lines here are going to be almost parallel. If we draw a line perpendicular to this one is going to also be almost perpendicular to this other line, right? And the difference in path lengths, instead of being d1 minus d2, is going to be this little difference that you're seeing there. We do that because we can get a simpler equation to model what's happening right in here, okay? If you want to do, d1 minus d2, you're going to do, but you can't do it. But then you're going to get square roots in there. That's going to be difficult to treat mathematically. So instead, we get something much simpler than that. This d1, let's see here. Yeah. Okay, and now we have the following. We can state that this distance here is going to be approximately d1. D1, no, d2, right? Yeah, it's not d1, it's d2. It's going to be approximately d2. This one is d2. A little mistake in there. And let me get an approximation. Okay, approximation sign here. Green. Okay, and now we have this guy here is going to be d1 minus d2. I'm going to put this one far away here. And then we're going to have this right angle triangle. What we have here, a right angle triangle. That's d1 minus d2 and L, right? d1 minus d2 and L. 11:27. Let's see if we can finish before we go into our break, half an hour break. Okay. So here we go. Let's see if I have a nice drawing here. Okay, I have a better one. Let's see. Yeah. Okay, so this angle here, let's go back here. Okay, this angle is going to be approximately 90 degrees. And so is this one, approximately 90 degrees as well. It's all an approximation, okay? A good approximation. It's not any type of approximation. It's a good approximation. Let's see here. No, it's this one I want to deal with. Yeah, I'm going to get here. You go, 90 degrees. Approximately 90 degrees here as well. Okay, should be an approximation, okay? Maybe I should put, when I put like that, here you go. Approximately 90 degrees. Superscript, here you go. Black. So because this one is approximately 90 degrees and this angle here is theta, so this angle here should be theta as well, right? Now we have this right angle triangle here. Let me draw this right angle triangle in the next drawing. Here we go. I'm going to D, right? Here you go. I'm going to exaggerate this triangle. Even better, I'm going to use what's already available here. Shape that's already available here. Let's see a right angle triangle here. I have a right angle triangle somewhere here. Can't find it. Okay. Oh, here you go. Right angle triangle here. Okay, like that. I'm gonna no. Right there. Okay, now I got it. That's what the right angle triangle is all about. Okay. I'm exaggerating, like I said, you know. Like that. It's not exactly the same angle, but you got the idea, right? Okay. This angle that you see there is going to be approximately theta. Here you go. Like I said, you can do the exact solution for that, but you're going to get a very large equation. So you're better off doing this approximation. D1 minus D2 would be the exact solution, right? So here you go. And now let's, I'm going to put like that. Here you go. Okay, this distance here is going to be D. That's an unfortunate value, right? Because I put D1 and D2 there. This distance here is going to be D, and this difference in path lengths, D1 minus D2. Don't forget, it's an approximation. D1 minus D2. I'm going to make everything dark. Here you go. Right angle triangle. I'm going to use that. Here you go, right angle triangle. Okay. So 11:33. Let's go a little bit longer so we can finish that. Depending on the position of this, the position along the screen, the path length of the light from one slit will be different from the path length from the other slit, right? Because L is much greater than D, lowercase d, right? The angles that the angles the line of the lines connecting each slit to the same position along the screen are almost the same. almost the same. Okay. For this reason, we can come up with an approximation for the path length difference of the two waves. Here you go, path length difference of the two waves. And that is going to be, here you go, D2 minus D1 minus D2, right? Is approximately, here you go, is approximately what? Take a look at the drawing again. Sine of theta, here you go. D1 minus D2 divided by D is sine of theta, right? D1 minus D2 divided by D is going to be approximately sine of theta. There you go. Where sine of theta, you know, is going to be this angle that we span through the screen, right? Where theta is going to be this angle that you scan through the screen. If we come up with a, here you go, with a coordinate system here, okay, same thing, right? This theta here is going to be the same. Here you go. Well, this one here. Here you go. Same theta, right? We can make our origin of our y-axis. We can set up a y-axis here along the screen, and that would be the origin of the y-axis, right? Below is going to be negative, above is going to be positive, right? So that what you have. Okay, and what else? So let's go one more step here. We're going to write down like that. Is the difference in path lengths. Okay, what else can we do? Okay, if D1 minus D2 is equal to an integer of a wavelength, okay, we have if, you know, if D1 minus D2 is equal to 1 lambda, oops, 1 lambda, 2 lambda, 3 lambda, so on, you know, n lambda, we have constructive interference. We have constructive interference. Okay. Don't forget it's an approximation here. On the other hand, if is approximately, let's say, half of a wavelength, right? 3/2 of a wavelength, 5/2 of a wavelength, and what else? 2 n plus 1 divided by 2. Okay, we have destructive interference. We have destructive interference. Okay, so here you go. Let's write that down. Constructive interference. Let's summarize here, right? So you can go in our break. Constructive interference. Go. Destructive interference. Interference. N equal to 0, 1, 2, 3, so on. Okay. That's how we model the Thomas Young experiment. Any questions about that? Yeah, that's right. Okay, so we can, let me show you, before we go into our break, let me show you more or less what it looks like, the fringes, right? The fringes look, you saw the fringes there in the video, right? But the fringes look like that. There's a drawing, it's easier to understand. You go, a brighter spots that decrease in intensity as you go further. Here is the maximum at the center. Okay. At this spot, the path length from the first slit to the screen and the path length from the second slit to the screen are exactly the same. At this brightest spot, the phase difference is 0, but the path length is different, right? Path length different, but the phase difference is going to be 1 wavelength, 2 wavelengths, 3 wavelengths, and so on. Okay, and we have this dark spot here, this dark fringe, not dark spot, but a dark fringe here in between. So that's what we have for today, and this 11:40 already, right? Let's meet. If there's no questions, another break, 30-minute break. We meet again 12:11. Okay, 12:11 p.m. Let's have our lunch and we meet in half an hour. See you then.